Okay, and we're live. Another Sunday. Oh, why did it stop sharing my screen? What a mess. Okay, so this time I didn't have a lot of time to think about what I was going to stream this week. So I realized I already started covering determinants. And that's in the course I'm TAing. That's about where we're up to in the course. So hopefully I'll have some viewer questions, some more viewer questions today, like specific things from the textbook or maybe just topics. So with that being said, I guess we can jump into here. I would go ahead and jump to section 4 about Rn, although I don't want to get too ahead of myself. I know that maybe some people have midterms coming up, so I think it'd be worthwhile if I reviewed some things to do with things that you can expect on some of these midterm type questions. So I think we already talked about elementary matrices as well. But maybe it's good to just walk through another example of that, just because I know I had a number of students last time having issues with problems about elementary matrices, right? So let me open up my notepad here. And so look, we have a review of everything we did last time, right? So I'm going to try another one of these problems with elementary matrices. Last time we used these to find the inverse of a certain matrix, but there are questions from the textbook that look something like, suppose the reduced row echelon form of the matrix A is the matrix R. And then the question might say something, like find a matrix U such that A is equal to U times R. And if you tuned into the live stream last time, this is more or less the process that we use, say, to find the inverse of a square matrix. But we can solve questions like this even if A is not square. Of course, we can't find an inverse if it's not square, but we can still solve this problem. So what might that look like? Well, let's take maybe a 2x3 example. So let's do 2, 1, 3 minus 3, 0, 4, right? So this is our this is the matrix we'll be working with. And we'll start with this matrix here, and let's find its reduced row echelon form, right? So at this point, we should all be pros at doing this, basically. So what I might do first is I could take row 2 and simply add row 1. So go row 2 plus row 1. And this will give me, so row 1 is not changing in this step. Row 2 becomes -1, 1, and 7. So then, okay, I've got a 1, but it's not quite, I've got this entry, which is a candidate for my leading one. But of course, I need it to be positive. So I'm going to multiply row 2 by -1 to give me 2, 1, 3, 1, -1, -7. And I want my leading one to be up top. So then I'll go row 2 swapped with row 1, which will give me 1, minus 7, 2, 1, 3. Please let me know at any time if you have questions in the chat. I'm going to be trying to stop and keep an eye on that. Okay, so I've got, in my first column, I've got the entry that I want to be my leading 1. So I want to knock out this 2 now. And I can do that by going row 2 becomes row 2 minus 2 times row 1. So simply applying this. Of course, row 1 is staying the same now. And this will become 0. This will be, so I'm going to have minus 2 multiplied by positive 1. So I'm going to be adding 2 in this case. So this becomes a 3. And then same here again, I have the double minus sign. So minus 2 times negative 7 is actually plus 14. So this will be 17 here. Okay, so now I've got, this is my other leading entry. I would like to make that equal to 1. So I'm going to go row 2 becomes 1/3 multiplied by row 2. This will give me 1 minus 1 minus 7, 0, 1, 17 over 3. And in order to get this in reduced row echelon form, now that I have on my second row, I have my leading 1, I want to make sure the entry above it is equal to 0. And this can be obtained by simply taking row 1 and adding row 2 to it. Of course, keeping in mind, the important thing now is that now that I have a 0 in this position, I don't have to worry about affecting my other leading entries. So this will be 1 plus 0 is 1, minus 1 plus 1 is 0, minus 7 plus 17 over 3, and this is 0, 1, 17 over 3. Right, so this is our reduced row echelon form matrix. So scrolling back up to the beginning of our problem here, so our A in this case is the matrix that we started with. And now our R is going to be this matrix. So I'm just going to simplify it a bit, right? So I want the denominator here to be the same, so I can combine these terms. So minus 7 is the same thing as negative 21 over 3 plus 17 is going to be 4 over 3, or rather minus 4 over 3, 0, 1, 17 over 3. So we have our matrix A from the setup of this problem. We have our reduced row echelon form matrix R. And now we would like to find some matrix W such that A is equal to U times R. And so there's a lot of row operations here that we have to go through. So let's see. This is row operation 1. This is row operation 2. This is row operation 3. This is row operation 4. This is row operation 5. And this is row operation 6. So the usual way that we could do this is we would take the identity matrix and form the elementary matrices corresponding to each of these matrix operations. So, for example, in this case, E1 would be, we take our 2 by 2, because remember that matrix multiplication, say for two matrices X and Y, this is only defined if the columns, the number of columns of X is equal to the number of rows of Y, right? So in this case, if we want an elementary matrix to be multiplying our A on the right and corresponding to these elementary row operations, then we know that its columns have to be equal to the number of rows of A, which is 2. And since these are elementary matrices, they're square matrices, so they're 2 by 2. Okay, so E1 will be the matrix where we apply the first row operation to the identity. So just to help you visualize this, remember the identity is this matrix 1, 0, 0, 1. So this will look like 1, 0, 1, 1, because we're adding row 1 and row 2. E2 is the matrix which we simply multiplied row 2 by -1. So this is 1, 0, 0, -1. E3 is simply the matrix obtained by swapping row 1 and row 2. E4 is the matrix obtained by subtracting 2 times row 1 from row 2. So this will be -2, 1, 1, 0. E4, or sorry, we just did E4. So E5 will be the matrix operation obtained by multiplying, oh, wrong row. And then finally, E6 will be the, again, this will be the same, or not quite the same. So now we're adding row 2 to row 1, right? And so, you know, we talked about this last time already, that now we know that E6 times E5 times ... times E2 times E1 times A is equal to R. And I could figure out the matrix U, right? So A is going to be just multiplying the inverse of this. So I could go E6 times E5 down to E2 times E1, and then take the inverse of that matrix and multiply it by R. And this will give me my matrix U in this case, right? But here's a problem with this. We can, this is a lot of work, right? So even though, you know, multiplication of 2 by 2 matrices in general isn't all that bad, but we're multiplying a lot of them together here. And then at the end of multiplying all of these matrices together, we then have to find the inverse, which again for 2 by 2 matrices isn't too bad, but it's also maybe not ideal. So the other thing we could try doing here is actually setting up a linear system of equations, or almost a sort of guess and check method. So what do I mean by that? So here, so A is 213 minus 304. So we want to solve, so we have 213 minus 304. And we would like a matrix. So I'm just going to write in some variables here: x, y, z, y, z, w, such that, so this is our A, right? And we want a u here, so that if we multiplied our reduced row echelon form matrix, which was 1, 0, minus 4 over 3, 0, 1, 17 over 3, to make this equation equal, right? So one thing that we could do in order to try and solve this is compute this, and maybe we'll be able to work out what some of these variables ought to be. So I'm actually going to do the computation on the right-hand side of this equal sign. So here I'm going to multiply across the row and down the column, right? So it's going to be, that's just going to be x. And then I'm going to multiply across the row and down the column, which is just going to be y. And then I'm going to multiply again across the row, down the column. And that is going to be a minus 4x over 3 plus 17 over 3y. And I do the same thing for the bottom row, right? So I'm going to go across and down, across and down, across and down. And what I'm going to get is zw minus 4 over 3z plus 17 over 3w. And now I just have to compare both sides of this equation. And what's nice about this is I can read off this solution pretty easily. Because if I look here in the first entry, here I just have x and I have 2. So this tells me that x has to be equal to 2. Here I have y and 1. So this tells me that y has to be equal to 1. Likewise, z has to be equal to 3. Minus 3 rather, and w has to be equal to 0. And sure enough, this is so our answer then in this case, if we want to find A equal to U times R, well, now we know that the matrix U equal to 2, 1, minus 3, 0. This is the solution. Okay. Well, I guess, so homework, maybe, let's say, check this. Right, multiply A times this U and see that it works out. Or the other thing to check, if you're really bored, try and you really want to practice your 2x2 matrix multiplication, you can try this other method. You multiply all 6 matrices together and then take their inverse. So, of course, yeah, let me know if you have any questions or if you want to see anything done from a particular section of the textbook. So last time we already talked about the determinant. So maybe let's talk about finding the determinant of a matrix using row operations. So we haven't discussed this yet, and this is important. So you should expect there to be some connection, hopefully, right? So as I had mentioned before, in last week's video, we had this result where we knew that for an arbitrary matrix A, we knew that the A inverse exists if and only if, right? Sometimes we use this double arrow, or mathematicians will spell if with 2 F's, if and only if the determinant is not equal to 0, right? And so there's something to do with the inverse of A existing and the determinant not being equal to 0. But we also have this other method of finding the inverse, right? So we know that if we start with the augmented matrix A and then the identity matrix on the other side, and if we do row operations to get A into its reduced row echelon form, and then we get some matrix M on the right here, well, then we know that we have this other statement that A inverse exists if and only if the reduced row echelon form of A is equal to I. And then in which case, then we know that M is going to be A inverse. This is going to be the matrix that we're looking for. So if we follow this arrow now, our row operations, right, to get down to reduced row echelon form, this does tell us something, right? We know that we can figure out whether the determinant is not equal to 0 or not based on what happens under the row operations. So a natural question might be, well, okay, that's just one value, right? We can just tell yes or no, is the determinant equal to 0? But is there a way that we could use row operations to help figure out the determinant in general? Well, the answer is yes. So if we look, I mean, that's the whole reason why we have this section here, finding determinants using row operations. So let's go down, and there should be a statement here that tells us the particular rules. No, we're just right into the exercises here. So let's see. One second. Oh, here it states it in the other theorems, right? So we have a couple different results, right? So first we have a theorem. So we have 3 row operations, right? Our row operations are, one, we can swap rows. 2, we can add multiples of a row to another row, and 3, we can also multiply a row by some scalar value. So all we really need to know is we need to ask ourselves, well, what do each of these row operations separately do to the determinant? So as you might have just read before I changed the screen away, swapping rows has the effect of sorry, my brain stopped working for half a second. Has the effect of introducing a minus sign there. So let's say if we do a row swap between a matrix A and the resulting matrix is called B, then we know that the determinant of B is going to be equal to the negative of the determinant of A. Okay, so let's figure out what happens to our other 2. So multiplying a row by a scalar, right? We see let A be an n by n matrix, and let B be a matrix which results from multiplying some row of A by a scalar k. Then the determinant is equal to, it has the overall effect of multiplying the determinant by k, right? So this is what I had written in my list here as part 3. So this says, if A is obtained by, we take some row, and that row becomes k times that row, and the resulting matrix is B, then we know the determinant of B is simply equal to k times the determinant of A. And then finally, for the last row operation, scalar multiplication. Oh, hang on a second. Okay. Yes. Sorry. This is a generalization. We'll come back to that in a moment. But for the basic row operations, what we need right now is adding a multiple of a row to another. And this is an interesting property because this one doesn't affect the determinant at all, as we can see. So if our third operation here was A, and we did, row, some row, let's call it row dot, becoming row dot plus k times row, I don't know, double dot, then the determinant of these 2 matrices are the same. So how can this help us? So here's all these fancy properties, but how does this help us? Well, remember last time when I talked about cofactor expansion, right? If we're trying to figure out the determinant of some 4x4 matrix, let's say 1, 2, minus 1, 0, 3, 0, 0, 2, 0, 1, minus 1, 3, 0, 1, 0, 4, right? Let's say this is the matrix and we want the determinant here. So again, because cofactor expansion, remember, we choose a row and we sort of proceed along the entries of that row, and then each of the cofactors are going to be multiplied by the elements of that row, right? So if we picked like the ith row, we're going to have ai1 times the cofactor of ai1 plus ai2 times the cofactor of ai2 plus dot, 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 dot. And the point is we want to pick a row that has a lot of zeros, because if any of these entries are zeros, then it doesn't matter what this cofactor is going to be, right? Because it's just going to get multiplied by 0, and we don't have to bother doing the calculation, which is great, right? That's saving us a lot of time. Determinants take a lot of time to compute. So, for example, in this case, I would suggest doing cofactor expansion along either row 2, because it has 2 zeros, or row 4, because it also has 2 zeros, right? So these are tied for the most number of zeros. And then the second thing I would go to in the case of cofactor expansion is I would look at which one has the bigger numbers, right? Because of course, bigger numbers, harder to multiply in your head. This one, I would say it's kind of hard to tell. It's more just like, just pick one, whatever one gives you the better vibes. Because for instance, I mean, both, like this has 2 and 3, but this has 1 and 4, right? So, okay, 4 is bigger than anything else here, but it's not much bigger. And then the advantage is this row has multiplying by 1, which doesn't do anything. So that doesn't have any work. So I might actually, even though 4 is a bigger number here, I might actually choose to do cofactor expansion in this case along this row. And you know what? It's 4:30, so why don't we do cofactor expansion? Why don't I walk through this example? And yeah, I'm gonna walk through this example. So let's do it. Let's do cofactor expansion along this row. I'm gonna erase some of these lines here. So what does cofactor expansion look like in this case? So first we have, this will be 0 times the cofactor of, I don't know, we'll call this A41. So I'm not even going to bother writing it out, right? Because we're multiplying by 0. So no big deal. So this will be plus 1 times, so again, since it's 1 multiplied by something, I don't need to bother writing out. So we'll have the cofactor of A42 plus, again, this will be 0 times the cofactor of A43, which I'm not going to bother writing out because, again, it's just multiplication by 0, plus 4 times the cofactor of A44. Okay, so expanding this out then, right? This first term is 0. I can forget about it. The next term, so this is going to be minus 1 to the power of 4 plus 2. So that's minus 1 to the power of 6, multiplied by the determinant of the cofactor of this entry, right? The cofactor of 4, 2. So I block out these entries. I block out these entries. I look at the matrix that I get. So it's going to be 1, 3, 0, minus 1, 0, minus 1, 0, 2, 3. Plus, okay, the next one again is multiplication by 0, so I can toss it out. Plus 4 times, so it's the cofactor of A44, so it's going to be minus 1 to the power of 4 plus 4 is equal to 8, multiplied by, and now I'm still knocking out this bottom row, but it's the 4, 4 entry, so I'm now knocking out the 4th column, and this is going to be the determinant of 1, 2, minus 1, 3, 0, 0, 0, 1, minus 1, right? So that's pretty nice, right? Like if I had picked a different row, I would have had another 3 by 3 determinant here. Well, if I'd picked row 1 or row 3. Let me give a second to check on the chat and make sure nothing's crashed. Okay, great. Okay, so now we can go ahead and compute these determinants. But we can also do this using the trick I told you last week, right? So we can write these out as, say, 1, 3, 0, minus 1, 0, minus 1, 0, 2, 3. And then we put a copy of the first two rows beside. Maybe I shouldn't use green because I like to use that for the arrows. What's another color here? Pink is nice. So what am I putting here? 1, 3, 0, minus 1, 0, minus 1. And so now computing this determinant, let me get my red back though, because I like that for subtraction. So I'm going to add multiplying along each of these diagonals. So I'm going to have 1 times 0 times 3, right? I have a 0 in there, so that's just going to be 0. I also have a 0 in this in the second downward arrow. The last one is 0. And this third downward arrow starts with a 0. So I'm actually going to get no contribution from the positive part. So on to the negatives. Again, so this is 0 times 0 times 0. Great. That's just 0. I have 1 times 2 times minus 1. So 1 times 2 times minus 1 plus negative 1 times 3 times 3 plus negative 1 times 3 times 3. Okay, so this determinant is going to be, so I still remember I have my negative sign in front because now I'm going down into the left. So negative, this is just 2 times minus 1, so this is negative 2. This is negative 1 multiplied by 9. So this is the negative of negative 11, which is positive 11. Okay, so let's compute. So that is the determinant of this first 3 by 3 matrix. Let's compute the determinant of this next 3 by 3 matrix. So we have 1, 3, 0, 2, 0, 1, minus 1, 0, minus 1. And again, I just am going to add the first two columns, write them down again beside this matrix, and do my usual trick. So again, oh, look, I have a 0 along this line. I have a 0 along this line. So those contribute nothing. And then my first entry that isn't just 0 is minus 1 times 3 times 1. And that's it for the positive contribution. Then minus, and I put a bracket here. Well, again, this downward diagonal has a 0. This downward diagonal has a 0. And then finally, I get a non-zero entry, which is 2 times 3 times minus 1. So simplifying this expression, this is minus 3 minus 2 times 3 is 6, minus 1 is minus 6. So this is negative 3 plus 6, which is positive 3. Okay, so now we can substitute these values in this equation above for this determinant and this determinant. So writing an arrow to bring down my calculation here. So remember, a negative number to a positive to a even exponent is always even, and if it's to an odd exponent, Sunday nights, my brain's not working. Minus 1 to the power of even. Some even number is always going to be positive 1, and minus 1 to the power of some odd number is always going to be minus 1. So this just becomes the determinant here, which we figured out to be 11, plus 4 times, again, this is going to be positive 1. So this will be 4 times 3, which is equal to 11 plus 12. And that gives us a final answer of 23. So our final answer for this question, this matrix that we started with up here, our final answer is that the determinant is equal to, what did I just say, 23? Yeah, 23. Okay. So, and maybe I'll use this as an example because we'll see an even easier way, believe it or not, to determine its determinant. So the point of all of this being, so main point is that cofactor expansion is easiest along a row of zeros. So with that in mind, right, what would be the easiest is, well, now for some of these big matrices, right, so cofactor expansion can suck sometimes for a 4x4 matrix. But now what we have in our toolkit is we know that we can make a matrix simpler by performing row operations. And sometimes we'll get an entire row of zeros if we do row operations, right? And we have the added benefit of now we know exactly how the determinant changes if we apply a row operation. So putting all this together, what that means is if you have some big complicated, like a 4x4 matrix or a 5x5 matrix, you know, here at least the example we did, cofactor expansion is not so bad. We had some rows of zeros to cofactor expand along. What if you didn't have that? Well, what we could do is we could perform row operations and get to get a simpler matrix, solve the determinant there, and then we simply know how we have to augment that determinant to get the original determinant. So let's look at an example like in this case. Do I have a copy tool? I probably have a copy tool here. I can just like lasso this matrix. Sweet. And now I can just drag and drop this down. If my twitchy screen will let me. Great, great. Ooh, went too far. Okay, here we go. Right, so I'll just drop this matrix down. Just makes it easier to look at here. And let's see, can I just delete these? Yeah, great. So here's my matrix. And let's try getting this in reduced row echelon form. So we're going to get more practice doing that as well right now. Sorry. Probably drink some water. It's good to stay hydrated, especially while doing math. Okay. So what we can do, well, if I look at this matrix, right, the first thing I do is I look at my first row here, and I see I have a 1. So I probably want that to be my leading one. So I've got to knock out this 3. So I could go row 2 becomes row 2 minus 3 times row 1, for example. So I'm going to get 1, 2, minus 1, 0. This will be 0. 2 times 3 is 6, so this becomes negative 6. 3 times 1, so here we have to be careful because here I have minus 1 and minus 3, so I'm actually going to be adding 3 in this case. And then the last entry is 0, so it doesn't change anything here. And then 0, 1, minus 1, 3, 0, 1, 0, 4. Okay, so now in the next one, I have actually I have like 2 choices. Do I want this to be my leading one, or do I want this to be my leading one? And the thing I would personally do is, since I already have a 0 here, and so another way to think about it is this row here has more non-zero entries. So if I were to knock out this 1 and choose this to be my leading one, I'm getting the added benefit of turning one of its non-zero entries into a zero entry. So that's what I'm going to do. So I'm going to go row 3, and I'm going to transform that into simply just row 3 minus row 4. So I'm going to get 1, 2, minus 1, 0, 0, minus 6, 3, 2. Here, I don't have to worry about anything because this entry is 0. So this will be 0, 0, 1 minus 0 is still minus 1. And 3 minus 4 is minus 1. 0, 1, 0, 4. Okay. Now, one thing I would actually recommend in these cases is it's not always necessary to determine to put answers to put leading ones in the like complete row echelon form, because then we're introducing the extra row operations of row swapping, which might get us confused with minus signs. So we should still, but I'm still going to, recognizing that this is one of the leading ones I want, I'm gonna go ahead and try and knock out both of these other entries here. So I could go row 2, of course, is going to become row 2 plus 6 times row 4. So what do I get here? I get 1, 2, minus 1, 0. Row 2 is going to be 0, 0. Here I have a 0, so that's not going to change the entry at all. And then 6 times 4 is 24, plus 2 is 26. And then 0, 0, minus 1, 0, 1, 0, 4. And then I want to go row 1 becomes row 1 minus 2 times row 4, because I still want to get rid of this 2 up here. So this is going to be 1, 0, minus 1, minus 8, 0, 0, 3, 26, 0, 0, minus 1, 0, 1, 0, 4. Okay. And then I look to my next one, and okay, so I've got in the first column I've got my leading one and everything else is equal to 0. In the next column I've got my leading one and everything else is equal to 0. In my last column, I want to get my leading one here. So I look, well, it's either going to be this 3 or this minus 1. And just the way I think, well, personally, this seems closer to being 1. So I'm going to simply multiply row 3 is going to become minus 1 times row 3. So we can see in this example, I am just using this matrix because we already computed its determinant another way, and this is a good way to check our work. But you can see in this case, cofactor expansion would be faster because we already had 2 zeros in place. But the point is if you had a matrix that didn't have any zeros in any rows, you could do even just 1 or 2 row operations, and then you're creating zeros in the rows and making an easier determinant to compute. Anyways, continuing along this process, now that we have our leading entry, I want to knock out the other all the other entries in it. So I'm going to go first. Maybe I'll do row 2 minus 3 times row 3. So I should specify row 2 is becoming row 2 minus 3 times row 3. So this is 1, 0, minus 1, minus 8, 0, 0, 0. This will be 26 minus 3 will be 23. 0, 0, 1, 1, 0, 1, 0, 4. And then I still want to knock out this one up top. So I could go row 1 becomes row 1 plus row 3. So I get 1, 0, 0, minus 8 plus 1 is minus 7. 0, 0, 0, 23, 0, 0, 1, 1, 0, 1, 0, 4. Okay. So one of the reasons why this is so great is, again, in this example, it's maybe not so clear why this is advantageous because we already had some zeros in a row to begin with. But imagine we didn't have any zeros, right? And we do these couple row operations, which hopefully you're experts in now at this point in the semester. And now look, now we have a row with 3 zeros. So it doesn't look like, because we have here leading 1, leading 1, leading 1, it doesn't look like we're going to be able to get rid of this 23 and turn it into a 0. But what we can do is we can multiply. I mean, we could turn it into a 1, sure. But even just doing cofactor expansion now, having this row of zeros here is going to make our lives way easier. So if we were to do cofactor expansion on this matrix, right, call this matrix B, let's say. So the determinant of B now, I'm not even going to write out the first cofactor terms, right? Because this first term is, we're just multiplying everything by 0. The next term we're multiplying everything by 0. The next term we're multiplying by 0. The only one we have to worry about is when we have this 23 here. So I'll just draw the line in for this 23. So the cofactor here is going to be cofactor expansion just becomes 23 multiplied by minus 1 to the power of, so what entry is 23? It's the 2, 4 entry. 2 plus 4 is 6. And then our determinant here is 1, 0, 0, 0, 0, 1, 0, 1, 0. And the added benefit that we get here, having done these other row operations, not only have we created this row of zeros for ourselves, but we've made a lot of other zeros in the matrix that weren't there before. So for example, when I go to compute this determinant, and using that same matrix trick, I will rewrite my first 2 rows beside here and go through the usual process. Well, look what happens. There's a 0 along this diagonal, a 0 along this diagonal, a 0 along this diagonal. So it's just 0. And then doing the negatives, I get a 0 along this diagonal. Here I actually get a 1 along that diagonal. So there will be a 1 in here. And then another 0. So there's this added bonus here. Not only do we have more of the constants being 0, making the overall computation easier, it's also making the 3x3 cofactor determinants easier if there's a lot of zeros. So here this just works out to being minus 1, of course. And so here we get our final answer of 23 multiplied by, so this is minus 1 to 6 is positive 1, multiplied by negative 1. And so our final answer is 23. So I realize we must have made a mistake somewhere here. Oh, wait. Right, this isn't our final answer. This isn't our final answer. So this answer that we got here, this is the answer for the determinant of this matrix, right? But that's not the matrix we started with. So in order to figure out what our final answer should be, we have to go back through the matrix operations to see what we did and how that might have affected the answer. Oh, hi. I see I haven't checked the live stream. So thanks for popping in. Yeah, I guess I need to watch the chat more carefully. I got carried away computing determinants. But so where are we here? So let's look at the row operations. I'm going to zoom out a bit, just so we can see all the row operations that we did. So here, right, what did we do? So let me scroll up for a second and let me remind you of how all the different row operations act, right? So as we saw, we have swapping rows. Simply adds a minus sign or multiplies by a minus sign. Adding multiples doesn't affect the determinant at all. And so this is actually the best thing ever, right? Because like, what are we actually doing? The row operation that we're doing when we're creating zeros, like above and below a leading one, that is the adding multiples of rows. So it's great because it's turning entries into zero, which is making our cofactors expansion easier to do. It's making the resulting determinants easier to do, and it's not affecting how the determinant changes at all. So this is like the greatest row operation. And then we also have adding multiplying a row by a scalar introduces a minus sign, right? So let's go down and let's go through all our row operations. And see what happens. So this first row operation, right, we're adding a multiple. So it doesn't change anything. This next row operation, we're adding a multiple. So it doesn't change anything. This next row operation, we're adding a multiple. So it doesn't change anything. This next row operation, we're adding a multiple. So it doesn't change anything, right? So we actually got, just from these first few row operations, we were able to create so many extra zeros without having to affect the value of the determinant. Now, this next row operation, though, this is the first place where we have to be careful because something's changing. So what this says, if we were to go back up and look at our rules, right? So so far, everything has the same determinant of A. But now if we consider this new matrix B, since the rule is if we scalar multiply a row, it scalar multiplies the resulting determinant. So what this means, actually, to write this out properly, even though so in the case this is just -1, but if the scalar had a different value, we'd have to be careful. So this tells us that the determinant of B is simply the result of performing that same scalar multiplication to the determinant of A, right? And why is this great? Because, well, if we look, our next few row operations, again, are just adding multiples. So nothing's going to happen, right? That doesn't change. That doesn't change anything. So it says that the determinant of this final matrix here has to have the same determinant as this B. And in other words, right, we found out that that determinant was -23. So that tells us that the determinant of B is equal to -23. And we know that that's equal to the determinant, the negative of the determinant of A. And so now I simply multiply both sides by -1, and I get that the determinant of A is equal to 23, right? And that is exactly what we found earlier through our cofactor expansion. So again, I really want to stress this point because you might be thinking right now, well, this other method seemed so much longer. It seemed like a lot more steps. Sure. I'm so sorry. I put my video screen in the wrong place. I know people preferred having it down on the corner. Forgot to do that. So sorry to anyone who prefers the larger screen. But the total point being that, yeah, this looked like more steps for the particular example that we did. But that's only because I wanted to start off by showing you an example of cofactor expansion where we can be smart about our zeros, right? If we didn't have any zeros in our matrix to begin with, we would want to create some zeros. And I'm hoping that by seeing this secondary method, you saw that we were able to create more zeros by doing this, and that it had this double effect of making not only less cofactors to compute, but making the computation of those cofactors that we had to compute that much easier. And of course, we got the same answer. So for example, like I would encourage you to try, like just write down, right? Just write down some arbitrary, don't make the numbers too bad on yourself, but write down some arbitrary 4x4 matrix and see if you can, that doesn't have any zeros in it whatsoever. Like try this matrix, and you could maybe like use a determinant calculator, right? So if you Google this, there'll be things out there that will allow like compute determinants of matrices for you. But then try this yourself. You should only use this to check answers, right? Because if you just get used to using matrix determinant calculators, you're going to be in big trouble when you've got to show your work on an assignment or a test. So try this by yourself. Use the method I used above, right? So get this in reduced row echelon form. Compute the determinant of the reduced row echelon form, and then use the rules from the textbook to figure out what the original determinant must have been. But I think that's going to do that. That's all for today. I know we're just shy of an hour here, but it's a beautiful day, and winter's coming. I'm going to go enjoy it. So thanks everyone for watching. Please, if you can make the live sessions next time, Sundays 4 o'clock. Please feel free to tune in, bring some questions, ask some questions. So I want to help you guys with like what you're struggling with, right? I'll always blab on about whatever questions each time, but I want to know what are the problems that all of you are having, so I can help you get better at solving those. Okay, so yeah, thanks, and